Okay, so in this video I want to discuss the use of lasers with the microbit itself. Now, before we kick things off, I'd like to first of all identify that lasers themselves can be very, very dangerous. Lasers, when pointed directly into your eyes, can cause damage to your eyesight, as well as you can lose your eyesight. So I'd strongly suggest that you handle them with due care and treat them like you would treat machines in the workshop themselves. You treat them with respect, you're careful when operating them, and follow strict procedures. Now, for this itself, I am going to show you how you can use a laser with the microbit controller, and to use lasers to form basically a detection system where the beam of light, when broken, will identify, that an object has passed through a particular area, a form of security system. Now, we have two different lasers here. They both do the same thing overall. They both, throw out a red laser light that can be seen. This one here does throw out a bit of a wider beam, and this one is a point itself that it throws out. Now, both these are fairly low voltage models. This is a 3-volt module, and this is about, I think, is a 3 to 5 volt module, but I tend to keep them at 3. And being such a low voltage, it works perfectly with the 3 volts that are thrown out from the pin here of the all-in-one breakout board, or the actual microbit itself, where you can see here it throws out 3.3 volts. So what we're going to do is we're going to use these in conjunction with an LDR. So I have an LDR over here. And what we're going to do is we're going to shine the light down on top of the face of the LDR itself, to indicate that, there's a laser pointing at it. And then when we're going to break that laser, it's obviously going to drop down what the resistance is from the LDR itself. And then the microbit itself can say that, oh, there's no laser touching off the front of the LDR anymore. And then it can, do something else, maybe a beep, or it can display something up on the screen itself. So to do this, we're going to basically follow this wiring diagram. As you can see, we're using our Keytronic all-in-one breakout board, which our microbit will be slotted into. We are going to have between 3 and 9 volts going to the Keytronic all-in-one breakout board itself. That's going to supply 3.3 volts to the microbit. And it also gives us all this additional functionality with the additional pins below here. Firstly, we can set up our laser itself. So for this bit of a circuit we're going to make up, I'm going to use this laser here. It's going to take 3 volts. The 3 volts is going to come straight from the 3-volt pin directly up to my laser. And then I'm going to have my ground, which is going to go to the black wire of the laser itself. So we have our red wire and our black wire here. Then we're going to additionally have our LDR. Like previously discussed in the other LDR videos, we're going to use a 10K resistor just to ensure that any of the voltage coming back to the board itself doesn't exceed a certain limit, which could damage the pins going back to the microbit itself. So we put in this 10K resistor going back to ground. We wired up the same as we did with the LDR previously. We have pin O going all the ways to one leg of the LDR. Then we have the 10K, which is connected to that as well, all the ways back to ground. I'm sharing the same ground wire here. And then on the far side, we just have our 3 volts coming to LDR itself. Okay, so let's put that together. Okay, so to put it together, I 3D printed this small bit of a test rig. You'll notice straight away that I've also put in this bit of a shield. The reason I've put in the shield is just in case the light goes beyond the sides of the LDR itself, which it should do, that it has a surface behind it that stops it from continuing elsewhere in the room, just for safety purposes. As well as that, I've securely held the laser so that it can't maneuver itself in the direction that it is pointing. And also I'm wearing protective glasses just to ensure that any light that bounces off will not damage my eyes. Now, the laser light itself is very, very, very weak in comparison to some of the ones, let's say, for instance, using a laser cutter or so on. But all the same, we're going to use, I suppose, the highest quality or the highest standard of safety when operating a laser. Now, what we can do is we can compare this to the diagram itself that I previously showed you. We'll start off with the most simple part. We have our 3 to 9 volts, which will go to the board itself. That's going to come in here from this wire. Then we have our wires going to the laser itself. So we have our wires coming back. You can see that they travel all the ways in here. And they actually connect directly back up to the ground itself over here. And our 3 volts, which is here. Now, the 3 volts is actually shared with the LDR. So you'll see that this line comes over here. So that 3 volts is actually shared and it comes in here to our LDR, as you can see. If we go to the opposite leg of our LDR, which is inside here, it's connected to our 10K and our 10K across to the ground, as well as our signal wire, which comes all the way back to pin 0, pin 0, whatever you'd like to call it, on the microbit all-in-one breakout board by Keytronic. So what we'll do now is we'll travel over to our microbit code editor and we'll put together a bit of code and come back and see how it works. Okay, so now that we've moved over to our microbit code editor, we can start off by deleting the onStart block. So drag that over here and delete it. And we'll just work with our forever block because that's all we need for this line of code. We can go down to our logic tab. We can select our conditionals, which is this if block here. Drop that in. Now we don't want this true inside here. So what we do is we go down to logic again and we go to a comparison block and drag that up and drop it in here. Now, what are we going to be comparing? So we're going to be seeing what value the LDR is giving. So an LDR, basically the resistance of the LDR increases and decreases depending on the light value. Now our light value is going to be determined by the light of the room, but more importantly by the laser pointing at it. So the laser is such an intense light, it's either going to be, a high resistance once the laser is on it, or a low resistance when the laser is not on it. Although that can vary, it will be such a large variation between when the laser is on it and not on it that we can set it up that it only really takes note of the laser itself because it's so intense compared to, the ambient light around it. So let's start off by putting our laser value in there. Now, the LDR value. And the LDR value, we're going to have to use the pin that it's coming back to. So if we drop down here and go to pins, and we want an analog read pin. We don't want digital because the signal coming back from our LDR is going to be an analog signal. So we grab that and we can put it in here like so. And we want to identify if it is less than 800. Now the reason I picked 800 is because it's a nice value that it has a good bit to go above that if the laser's on it, and a good bit to go below that if the laser's off it. Now, if this is true and pin or pin 0, whatever you'd like to call it, is less than 800, that means the resistance is high. And that means, the resistance is low. So that means that the laser, in fact, has been taken away from the LDR, or it no longer can find its way to the LDR. So that means that that laser light has been broken somewhere between the path of it traveling from the laser to the LDR itself. And if that happens, we're going to say that, the intruder's there maybe, or for instance, a customer has opened the shop door and then basically then rings this noise that either alerts the authorities, rings this noise that alerts the shopkeeper that someone has entered his shop. So let's go for a bit of a noise. So we can go to music. We'll just go to something basic where it will play a sound, like so. Drop that in there. And just go and press this plus signal, see what the starting frequency, end frequency, and duration will be. That's absolutely perfect. This is the noise it's going to make. I'm not too sure if you can hear it. It's a bit of a do. But what I can do is to stop that from playing, so I can press this box over here just to stop that sound for now. And that's all you really need for this to work. Now, if you like and you want to show the value up on the 5x5 matrix that's being given, and you can do that by just putting into your basics here, show a number. We'll duplicate this analog read pin or pin 0, and we can drop that in there. And basically what that does is it shows us the value. And for instance, if this sound isn't working, we can see what value's on it when the laser's on the LDR and when it's off it, and then adjust our value here to identify when the laser is no longer on it. But I've already tested this previously and I know 800 works very well. So what we can do is we can upload that to the microbit itself and we can see how we get on. Okay, so now that we have our code uploaded to our microbit, we can connect a battery. So we'll just connect this 9-volt battery here. I'm going to be careful that I have my glasses on. I have my laser mounted in such a position that it is only going to shine light directly at the LDR, which is right here, and any light that bounces past it will be protected by this screen itself. So as you can see there, you can see how the laser is actually on the LDR itself. And if I just turn it off quickly, you'll see how it's gone, and it's back on there again. And you can also see that there's no light passing behind this shield itself. The shield is stopping it from getting anywhere else. Now, if I put my hand in between the laser and the LDR, it will be basically breaking that laser, and the LDR will no longer be getting any light, and you can hear the buzzing noise from that. When I take it away, again, the light is now increasing the resistance in the LDR, and it is stopping the beeping itself. The value obviously has changed, so the beeping is stopped according to our code. Now this, you can imagine, could be spread across a room itself, and let's say if you had a theft, robber coming in, he broke the beam, it would make the noise. And when it's not broken, it won't. So for instance, you can have that set up to a continuous alarm. When it's broken, it would keep going off even if the light went back on it. But for this case, anytime the light is broken, it makes the noise. Another example of where this could be used, for example, in a shop, you could have it up high above the door, and when the door is opened, it could break this beam up high, and it could just bring your attention that a customer's after walked into the shop itself.